Welcome to the short presentation Increasing the Durability of Inserts for Aluminium Die Casting by Means of Conformal Cooling. Here I want to show you what the causes of premature failure are and what possible solutions there are. Let's get started. The durability of inserts with conformal cooling is currently limited. This is due to various causes which are discussed in more detail here. The following damage patterns occur. Once there is a crack due to thermal stress, high temperatures in aluminium die casting are unavoidable and those thermal stresses are relevant. The second point is corrosion. Once by the high water temperature, but also by the wrong choice of materials. If a hybrid base is made of 1.2343 and the contour of 1.2709, the 1.2709 acts as a sacrificial anode and dissolves. The third common cause is cavitation. Simply too much heat is carried into the water and the cavitation destroys the insert. Let's go through the points in more detail. At high temperatures, the reaction rate increases and the water molecule can break down into a positively charged hydrogen atom and a negatively charged OH group. Both react with the steel. The problem can be solved by means of coating. If the water temperature is too high, cavitation occurs. Locally, the evaporation temperature is exceeded and a vapor bubble is formed, which collapses again. Sounds harmless at first, but this process attacks the structure and breaks out individual grains, which accelerate the process. A coating does not help at all here, as this is also destroyed. This can be prevented constructively and checked by means of simulation. Thermal stresses result from uneven tempering. Some areas expand more than other areas due to the temperature increase, and this leads to stresses that exceed the material strength. A crack is the result. Let's take a look at the theory of thermal stresses. As already described, thermal stresses are the result of strong temperature differences in short areas. On one side, there is a high temperature or heat source, and on the other side, there is a lower temperature or heat sink. The warm material expands, and in the cold area, it shrinks. The result is thermal stress. If there is no notch in the component, the thermal stresses are comparatively low. However, if I have a hole, for example a cooling channel, in the insert, this is already a notch, which increases the stresses. If there is a high temperature gradient, the stresses are also high, which can lead to failure. If I want to reduce the stresses, I have to decouple the thermal expansion. This would be possible via large area cooling, but this is mechanically unstable. I also need a special temperature gradient, but this is not feasible with a resulting flow. One possibility for a solution is to have several channels with a small distance between them. In this way, I achieve a similar effect as large area cooling. For this to work, high volume flows, the smallest possible deadwater areas and small diameters are necessary. The smaller the diameter, the smaller the notch number and this lowers the stress further. What does it look like in a real example? Here is a conformal cooling system with 3 circuits for aluminium die casting, constructed with the classic rules resulting in a flow rate of 16.4 liters per minute. If this cooling system is now simulated, there are strong temperature differences in these areas. Temperatures of up to almost 180 degrees Celsius are also present, so we have cavitation at high thermal stresses. This can be seen very well in the cross-section where stresses of 2010 MPa occur. This stress is in the range of maximum tensile stress for 1.2709, and with a hole as a notch, the maximum stress drops again, which will cause the crack here. The insert will therefore fail prematurely. For this case, the conformal cooling channels are redesigned. 3 circuits become 4 and small adjustments are made to reduce the flow resistance and increase the flow rate. Instead of 16.4 liters per minute, 30.5 liters per minute now rush through these cooling channels. If this new conformal cooling design is now simulated again, there are still small temperature peaks in one area, but this can be solved by design. What is relevant is the area where the crack originally started, and here we see a very homogeneous temperature distribution. This means that the stresses must decrease. And this is what we do. The stress drops so much that it's absolutely uncritical. The material is not stressed by the thermal stresses and the insert experience a long service life. Of course, the issue of cavitation has still to be solved here, but the main cause for failure has been solved. But what is the comparison between conventional and conformal cooling? Here's an example where conventional and conformal cooling is used. During the cooling phase, 2 critical areas are present. One is the cooling zone, where the stresses are 1600 MPa high, which causes a crack to start. Secondly, in the contour area, where a stress of minus 830 MPa is present. From the crack mechanics, very similar stresses follow for both areas, which means that the insert can fail at these 2 points. A conformal cooling is now introduced into this insert according to classical rules. There are 4 circuits resulting in a flow rate of 10 liters per minute. The CFD simulation results in maximum temperatures of 230 degrees in the water which makes cavitation relevant at this point. This must be solved constructively. The occurring stresses are pleasantly low and do not cause any problems. The main cause of premature failure, therefore, remains cavitation. I am applying the simple optimizations. This means reducing the flow resistance by increasing the bending radii so that the flow rate increases to 12 liters per minute to reduce the high temperatures. The problem with this design is that it makes better use of the water. The water temperature rises to almost 300 degrees Celsius, which means that cavitation will destroy the insert even faster. And on top of that, the thermal stresses are greatly increased to more than 2100 megapascals. This change to the design is therefore not effective. What about the cooling performance of the different variants at this point? The conventional design dissipates approximately 5 kilowatts of heat after 5 seconds. The progression increases slowly, which means that the design clearly limits the cooling capacity. However, the situation is different with the classic conformal cooling system. Here, the cooling capacity rises to more than 50 kilowatts and remains at that level. So I have a limitation due to the design and the material 1.2709. If I now make better use of the water, I can dissipate even more heat, but I also run into a limit. In addition to extending the durability of the inserts, another goal is to reduce the cycle time. If you choose expensive inserts, then you should get the maximum out of them. This way I can make a 19-fold parallel connection out of a 4-fold parallel connection. This achieves flow rates of 80 liters per minute, but the thermal stresses are still too high. If this design is now simulated, it still achieves a maximum cooling power of just under 110 kilowatts with a material 1.2709, but from here on, the steel starts to limit the heat transfer. If I now select a highly thermally conductive steel such as W36 for the same geometry, the cooling capacity rises drastically to a little more than 190 kilowatts. The curve also shows that the molten aluminium starts to limit the cycle time. Another problem with this solution is that it causes a high thermal stress. I can rarely balance the points of low thermal stress, no cavitation and short cycle times. What can I do instead? I accept the high stress and the resulting crack and control them in a targeted manner. In this case, the cracks will occur within the channels and only go from channel to channel. The hairline crack do not affect the flow rate, but make sure that they do not want to run in the direction of the contour. So I take the points of high cooling capacity and avoidable cavitation, but push the issue of cracks into a non-critical area. So the inserts will crack at some point, but not in the area of the contour. Of course, any weakness on the article that weakens the insert of the contour in advance must be also taken into account. Let's put it all together. With a material 1.2709, a significant increase in service life is theoretically possible, but cavitation throws a spanner into the works. I have to decide between durability or reduced cycle time. I can't get both together. Also, the heat dissipation from the aluminium is limited by the 1.2709. I can still transport a lot of heat energy out of the aluminium with a clever design, but at some point I will run into this limit. If I use a different material, such as W36, I can dissipate much more heat. The same design can dissipate about 90% more heat, and the heat transfer from the aluminium can become the limit. And with the new design rules, it's possible to handle the high stresses in such a way that the cracks run within a channel and from channel to channel, but not towards the contour. This makes it possible to significantly increase the durability. And it's also possible to suppress cavitation. A new material, which is currently being tested simulatively and practically, can reach a technical limit in aluminium die casting. However, this is still being tested. If you want to try this out ahead of time and secure a technical advantage, please feel free to contact me. You can also ask me further questions for this new method.